Okay, so in this video, we're going to talk about how to calculate one-way ANOVA, which is analysis of variance in Excel. And before we go over to the Excel table, I want to just look at some basics that we need to know for conducting our hypothesis test. So ANOVAs are done when there are 3 or more means to test against each other. So if you have only 2 means, you use a t-test. It might be paired or pooled or something like that, but it's going to be a t-test. When we have 3 or more, we're going to use ANOVA first because we want to know if there's any difference in the t-test rather than doing repeated t-tests for pairs. That's a lot of work, honestly. And there are issues with conducting multiple tests that statisticians worry about. The more tests you do, the more likely you are to just get something wrong by random chance. And so that can affect your results. And so we want to find a way to minimize the number of tests we're conducting. And if you have a lot of means, then of course, the number of possible pairs can be quite large. And so we want to know if we need to do all of that work in any case before we actually do it. So the ANOVA is a good way of just looking at all of our data collectively and identifying whether or not there is a likelihood that we need to care about the pairs. Which of the things are different, or are none of them different? So our null hypothesis assumes that all the means are going to be equal to each other. Again, our null hypothesis always contains the equality statement. The alternative is that at least one is different. Now, it doesn't mean that they're all different. They might all be different, but what it's going to mean is that at the minimum, one of the means is different from one of the other means. So I've written this out in sort of standard abbreviation math notation. It's not uncommon for students not in a formal statistics program to write these out in words, which is also okay, but do be careful because some students will get the ANOVA and the chi-squared test. They will confuse them or use the same phrasing for both of them. And that's bad because then we can't really know if you know the difference. So the null hypothesis is that mu I, so one of the means, is equal to mu j, another mean, for all I not equal to j. So if we have 3 means, essentially we're saying mu1 is equal to mu2, mu1 is equal to mu3, and mu2 is equal to mu3. All of them are equal. So for all I not equal to j, obviously mu1 is equal to mu1. So we're specifically specifying that any pair that we can come up with, they're all equal. And then the alternative is that for some I and j, there exists a mean from one group that is not equal to the mean of another group. So this backwards E means there exists a mean from group I not equal to the mean from group J for some. So that means at least one I and j not equal to each other. Now, mu1 and mu1 can't obviously be equal, can't obviously be unequal to each other because it's the same mean. So these are specifying, again, just that we're talking about different groups. So mu1 might be not equal to mu2, mu1 might not be equal to mu3, or mu2 might not be equal to mu3. Again, in this three sample example. But you know, this covers all of the cases. If we had 5 subsets, 5 samples, 5 means we wanted to compare, there would be a lot more combinations of mu1, mu2, mu3, mu4, mu5 that we would have to, again, theoretically spell out. But we're just looking in this alternative that one of them is potentially different. Now, we're making an assumption here that the standard deviations are equal. Now, what we can do is for an introductory statistics course, we can look at the box plots as an example to see if they're different The ANOVA test that we're going to calculate is going to automatically calculate all of those means and variances so that we can do that comparison. But a box plot is a nice way of doing this as a visualization. Now, there are hypothesis tests for determining if the standard deviations are sufficiently equal, but that's sort of beyond the scope of the sort of introductory business analytics types course. But it is an assumption that is worth worrying about because there are other ways of conducting one-way ANOVAs on non-parametric methods and things like that, which we're not going to talk about here. But that would be appropriate if this background assumption does not work. But we will examine it whether the assumption is met, but we're going to conduct the test as if we can make that assumption safely. All right, so let's go over to Excel and actually do the math. Now, if you have raw data, which this originally was, where you have a category value in one column, this is in this case age groups, and another numerical value that we can do an ANOVA test on in a second column, the best thing to do is to get these into separate columns for each group. This is also a good way of making a box plot. Sometimes I find Excel can actually figure out the box plot from sort of the unsorted, unorganized data, but it does a much more reliable job when you put them in different categories. And so what I've done here with this data is I've sorted it already, and I have copied and pasted. Then I have 3 categories: young, middle-aged, and older people. And then I've copied the salaries, just like literally copying, scrolling down until I run out of young, and then copying it into this column. ANOVAs do not have to have the same number of values in each of the groups. And so, in fact, it turns out that we do, in fact, have different quantities. There's fewer older people, and then younger people, and there's lots and lots and lots of middle-aged people. But that doesn't matter for Excel. Now, to do the Excel, the formulas are quite complicated to do by hand, and so we're going to let the data analysis toolpack do this analysis for us. So if we go to data and then select data analysis, assuming you have your toolpack installed, we're going to go to ANOVA single factor. Single factor is the same thing as one-way ANOVA. And we're going to select OK. The input range, now we can't just highlight the columns. We actually have to highlight down to the bottom of the longest column. I did highlight the labels in the first row, so I'm going to check that box. These are organized by columns. You can organize your data by rows if that's how your data is set up, that's fine. And then the output range, since I have only the one analysis, I'm just going to put it in the same workbook. Do be careful about where you place this. Because if you want to find it again later, you don't want it like 800 rows down. Alpha, it's going to do some calculations for us in terms of the significance cutoff value if we wanted to do sort of rejection region method. So if you're using a value for your significance level, which is different than 0.05, you can go ahead and change that value here. I'm going to just use the default for this example. Okay, so we've got our single factor ANOVA, and again, I'm just going to spread out these values so that they're easier to read. All right, now what the ANOVA is going to do is it's going to give us a summary of a lot of the values it's actually using in the calculation. So it's counted the number of observations in each of our groups. It looks like we had about 1,000 observations originally. Most of the time when you do ANOVA, you don't have that many. But if you have more than 40, you can't do them in your TI calculator. And so this is an alternative. It counts them, it calculates the sum of all of the values, it calculates the mean of all of the values, and it calculates the variance of each of the groups, young, middle, and older. Now, I find it really hard to look at variances and sort of eyeball whether or not these are similar enough. So I'm not even going to try. If you're going to try to do that, I suggest putting in your commas so that you can at least see if they're even on the same order of magnitude. We'll come back to that in a second. Now, if you're doing these calculations by hand, there's a bunch of stages to these formulas where you calculate between groups variation and within groups variation, essentially comparing these variances and comparing the means to each other. You compare the means of each of the groups to the mean of the overall data, and you create these series of steps. The sum of squares error, or the sum of squares, the sum of the mean sum of squares, and then the squares errors. Then you turn that into a ratio, which calculates your F statistic, and then that in turn is converted. It's F distribution is also typically a right skewed distribution, like the chi-squared test, but it has 2 degrees of freedom that are calculated from the number of groups minus 1 and the total number of observations minus the number of groups. So there's 2 degrees of freedoms that go into that. And then again, the ANOVA from the tool pack is going to convert this to a p-value. Now, there is, if you're doing these more by hand, there are distributions and things you can use in order to do these calculations if you want to. But they're really tedious. I mean, if you thought standard deviation was bad, try doing that 5 times in a row with 1,000 values. We've gotten this p-value, and the p-value obviously in this case is very small. And so what this is suggesting to us is, again, remember our null hypothesis is that all the means are equal. And if we're much below 0.05, then that's suggesting that there's really good reason to think the means are not equal. So for this example, given this p-value, we are going to reject the null. At least one mean is not equal to the others. I can spell. Now, which mean is not equal to the other? Well, that's not immediately obvious just from looking at the raw numbers, but we could maybe get a sense of it if we looked at the averages that were pre-calculated. The 2 that are the most different are the young and the middle-aged, but the only way we can really know if this is suggesting that one of them is different from the others, maybe young is different from middle-aged, but maybe middle-aged and older are not different enough to trigger it. The only way we could know for sure is to actually do our t-test. But what we can do is we can create a box plot from the same data, and at least we can give it an eyeball without going through the individual t-tests, paired t-tests. Sorry, they would be independent t-tests, but each pair at a time. So young with middle-aged, young with older, middle-aged with older. But let's look at our box plot and see what the box plot suggests. Box plots never come up under recommended charts. Here's our comparative box plot. And again, let's add a legend so I know which group is which. And we're going to give it a title at least. of salary by age. Now, if we look at these very carefully, as we noted, there is a distinct difference between the young and the middle-aged group. We saw that in the averages, that those were the two that were most different. So at a minimum, those two have been flagged as being definitely different. And we can see that like even the range in the middle 50% inside of our box is well outside the range of the middle 50% of our middle-aged box. So young is way down here, middle-aged is way out here. While there are some outliers, the ranges do technically overlap. The 27,000 that we had for our average for our younger category versus the average of 72,000 for our middle-aged category is significantly bigger. I mean, we're talking almost 3 times bigger. So it's almost certain that at least these two triggered our rejecting the null. It's less clear if these are enough to make that assumption. The middle 50% definitely overlap. The means are not as far apart. Now, when we do this test, on the other hand, the fact that there is so many data points, there's 500 observations in the middle category, because there are so many data points, we're almost certainly probably going to be able to detect a difference of like 20,000. But that depends on the variance. But that's a really big sample size for a means problem. And so it's probably going to be detectable given that this p-value is really, 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 really low. But if the sample sizes were smaller, then this would be more suspect. But again, the only way we can absolutely be sure is we can do paired t-tests. There are other methods like Tukey's method and things like that, but which we can also use, but which we're not going to cover here. Now, we also want to check our assumption about the variances. Now, I said that when we were looking at the variances up here, that it's a little hard to tell. And so I'm just going to go ahead and put in my commas. And they are, they're all kind of on the same order of magnitude. They're all in the, again, variances are squared values and our salaries are already big to begin with. So the variance here is in the hundreds of millions, but none of these are like 10 times bigger than the other one. That's not a great sort of eyeball way of going about it. These two variances do look much more similar, again, just based on the visualization on the box plots. The middle 50% range looks about the same. This one looks a little smaller, so I mean, I'm a little bit skeptical that the variance here would be the same as here. But again, if you're in a more advanced statistics setting, then you could do an actual hypothesis test on these variances to determine if they're close enough for our purposes. But it's always a good idea to check the assumptions. We can at least say here that while there's not an order of magnitude difference, visually, the young group does appear to have potentially a smaller variance. It's, it's smaller by like a factor of 3. And so that might be a meaningful difference that we would want to be potentially concerned about. And again, if this was a more advanced setting, we would want to test. But typically eyeballing it is sufficient for an introductory statistics level.